Hello, everyone. Good afternoon. I'm Bing Han. I'm Senior Software Engineer at Arimo. And today's talk is about how we can learn from smaller data set. How we can learn from a smaller data set in a deep learning framework with human assistance. Okay. And the outline of the talk, this will start with our motivation to doing this work. And I'll present our deep active learning approach, followed by the experiment results. And I'll conclude with a summary and future work. All right. So how many of you have seen this chart on the left? Cool. OK. Yeah. So deep learning is quite exciting. This chart is quite representative of the rapid development in deep learning over the last 5 years. So here's the classification arrows from the winners in the ImageNet image classification challenge over the last 5 years. And you see in 2012, for the first time, a deep learning solution won over traditional approach. And it has been the winning method since then, now even exceed human performance in object classification with regard to the ImageNet. Okay. The creation of the ImageNet dataset has fueled development of deep learning. It allows scientists to build more complex and deeper neural networks, in particular the convolutional neural net, and prove its effectiveness. Getting data is easy nowadays, but the vast majority of data is unlabeled. Having data labeled is costly. It's not cheap. It took the ImageNet project 2 years, recruiting 50,000 people through a crowdsourcing platform to label millions of images from the internet. And now it is the world's largest labeled image dataset. 6 months ago, I was part of the team from Arimo working with a global retailer on a wide range of machine learning applications. Using our machine intelligence platform, the system has to deal with an enormous amount of data, of product variations, product changes from historical data and a lot of new data coming in every day. And we were facing with a challenge of getting enough labeled data to train the most up-to-date model, the more accurate models for the business. And we were thinking, how can we still learn the small data sets that we have? And first we try to take as much public data as possible to train the neural net on that first, and use those to fine-tune with the small data sets we have. It didn't work so well. Okay. So that's when we thought of using active learning to be integrated in our deep learning workflow. So what is active learning? The idea of active learning is basically to reduce the number of labeled data needed in order to train an effective model. So instead of you picking randomly a subset of data to label, you can actively select the right ones to teach your models. Just like human, we learn faster and better with good examples. And it takes longer for us to learn from bad example. I didn't learn anything at all. So here's the active learning heuristic. It looks like this. You start with unlabeled data, a pool of all unlabeled data, all with some initial subset of data that is already labeled. when you have that initial data set, you can start training a classifier on the labeled data that you have. Now your data space is separated with the newly trained classifier. And from this point on, we think that there are those examples that are near the decision boundary that is considered the most uncertain one to the classifier, and we should pick those and ask human to label that and feed it back into the training loop to help improve your model. Okay. So we decide to integrate an active learner in our deep learning workflow. It looks like this. Okay. So here, the main component is still a neural network, and we want to train a neural network on the labeled data, the initial labeled subset of data that we have. Okay. After we train the initial models, we can take the learned embeddings at the last hidden layers as a representative vector for your data instance. Okay? So deep learning is good at learn abstract, high-level features of the data in that way, where the learned embeddings are very helpful later on. In this case, we have an active learner next to it, which basically do a clustering on the whole data set. So how can we do clustering on the whole data set here? Once you train a neural network, and you can run a forward pass through this neural net to extract the learned embeddings for the whole data set, and you perform clustering on that. And now our query of the most uncertain samples to label is actually cluster-based. When we have the clustering result, we compute the silhouette coefficient. The silhouette coefficient measures how good a sample is assigned to its current cluster. And those with the lowest silhouettes are those not well clustered. And those are considered the most confusing to your classifier. And we pick those and send for human for labeling. Maybe each iteration you pick 1%, 5% of your whole data set to get it labeled in that way. And you continue your training loop until your model converges, or until you reach the quarter of the number of samples that you can label. Okay. So we have tried this approach on several classification problems, and it works pretty well. For example, sentiment analysis, where there are a lot of product reviews, and you want to classify it whether it's a negative or positive review, right? And so with this active learning approach, we can train a reasonably good classifier, but we want also to see if it applies to another application other than classification. So if you look at this slide, here shows the search results usually Google return to you when you look for a particular product. For example, I search for a writing desk, and then it returns a set of products. Each product is represented with a photo and a caption, which is the product title that displayed to me. For example, this desk, right? The caption is mid-century vintage writing desk. So these are the type of product titles we want to generate for a new collection of products. So this basically maps to the application of image caption generation. Right? And so if you look back at the deep learning workflow I showed earlier, And there we had to adapt this neural network, basically trained to generate caption for a product. Okay? And so your data now is a pair of image and a caption that describe the image. And you want to use a convolutional neural net component in your neural network, right, to process the image from your data. And you also want to use an effective neural net architecture. Here is a recurrent neural net, in this case LSTM, which proved to work very well with many of natural language processing tasks. And so we want to use these two components to learn from the image and caption pairs that we have. So LSTM will take sequence and generate sequences. If you see a pair of image and caption, actually you can formulate a sequence out of it, with the first element is an image, followed by all the words in the sentence that describes it. Now, the first component here is a CNN encoder that will extract the embedding vectors for your image. And we also take advantage of word-to-vec model. So word-to-vec model is a language model that can learn the representative of words that are similar in semantics. It maps to a space that words are similar, that are close together. So we train a word-to-vec model on a particular, in this case, a particular marketing content vocabulary. So we can extract the word embeddings for the sequence of words for each image. So now we form a sequence of vector from the same embedding space. We start inputting the data into an LSTM to generate the sequence of text from that. In practice, this sequence will start with the image and followed by a special character to mark the beginning of your caption. And also at the end, there's a special character to mark the end of the sentence. Okay? So this diagram shows an unrolled LSTM component. Each LSTM cell would take input as one of the input vectors in the sequence. And the cell output will go through a softmax to predict the next best word. Once you run through this LSTM, the activation at the final cell's output, here, yn, can be used as the embedding vector that's representative for the whole data instances, include images and text, right? So that, we use that to do clustering for our active learner to actively learn the right next sample to label. Okay. So for this application, we have set up a small experiment to test the effectiveness of our approach. We have a training data set of 2,000 product image in a collection and the test data in 100 product images, right? And we want to test all these three approaches on this data. The first one, we want to train our text generator on the whole label data set, called fully supervised. Second, we want to pick 25% of the training data randomly to test a random labeling approach. And finally, we actively pick 500 samples labeled and feed into our neural network. Okay, So here's the results we get. Deep active learning shows quite promising results here. All these models are evaluated using the perplexity metrics, which measure how well a language model predicts the next word in a sentence. And the lower score, the better. You can clearly see deep active learning outperforms the random learning approach. Okay. And it's also very effective because just with 25% of the training data actively labeled, right? You nearly reach the perplexity of the fully supervised approach. Here's a closer look at the performance of these two approaches, deep active learning and the random learning approach. We have 8 iterations here. At each iteration, we ask for 50 more data samples to be captioned. And you see both these two models improved over time as it sees more data. But at every step, the deep active learning always outperforms the random learning approach. Okay, so if the model metrics are not convincing enough, let's look at some of the generated captions for this product, right? So on the left, we have the original product image. And on the right is actually the reconstructed image that our CNN components reconstructed from the embeddings of the image is generated. Okay, and you see the set of captions when the active learning approach is applied on 100 samples, on 300 samples, and when it sees 500 samples, the caption is really improved. So surprisingly, it learns very nice description of the product, right? So first show like hand cream stir senses, refreshing, sand and moisturize, soften skin. And so it improves over this caption when it sees more data. Okay. For example, the last one for just 100 samples, it confused these towels with kind of a dress, but it gets improved as more correct data were picked to get labeled. Okay, so a summary of this work. We have successfully applied active learning in our deep learning framework, and we have demonstrated an improvement of 3 times in perplexity score between the deep active learning and also versus deep random learning. And it's surprising that it turns out deep active learning works for text generation as well, not just classification. And it's quite effective when your data has clustering structure because our active learner is cluster-based. So if your data, in this case, has clustering structure, these products already belong to different categories, then you can apply active learning efficiently. Okay. For future work, of course, we start small with a small set of labeled data. We're planning to work on a larger scale data set to demonstrate the effectiveness of our deep active learning approach. Okay, so that's the end. Thank you. Any question? Yes?
How to deal with actual uncertainty in the sense that even the human would be uncertain what they're labeling?
So how do I deal with
True uncertainty.
the true uncertainty?
Yeah, where even a human would be uncertain what the object is.
That's a very good question. So that we just rely on like human expert to really get the label correct. Okay. Classify legal documents. You can not just ask anyone to annotate that, right? There's strong arguments, weak argument, the good law, bad law. So you gotta hire like human experts with law degree to correct that. Yeah. Sometimes there's confusing example, like the caption is really bad, and we find out that it's actually the image was not a good one, right? The background and the image itself just doesn't like match, for example. So we go back and correct that. Okay. Yes, please.
Yes, I have a question. Did you find that once you had the manually trained human labeled ones, that those were enough to improve the classifier performance alone, or did you guys also have to do a lot of hyperparameter optimization?
Yeah. Okay. So, would the active learner is enough to get the model improved, or we have to rely on other sources to improve the model? So it depends. If you pick the samples you pick are the representative for the whole data distribution, then you're good. For this one, actually, as I presented, we have to rely on a word-to-vec model, actually, to train on a larger corpus of all this marketing content, product description and stuff. So the model learns these nice words to generate caption for the product. For this one also, the image is quite simple. It's just an object with a white background most of the time, so show the product. So we can just train a CNN autoencoder on just the images we have. But for other more complicated image, we can just make use of other available pre-trained image model online like VGG, and we take that, initialize our CNN encoder, and fine-tune it. So, yeah.
So maybe can you hear me, Chris? 1, 2, 3. Maybe I'll also add that the baseline of comparison here, the basic idea here is when you have more labeled data, then of course it'll perform better. The idea is here, the main contribution here is to try to work with little labeled data. And so the baseline comparison is to adding more randomly selected labeling compared to one that is using this particular approach where you choose it where the using the silhouette score, things that are near the decision boundary, and the comparison is between that baseline of randomly selected label data versus sort of strategically selected. Hope that makes sense.
Any other? Yes, please.
I understand how this works in a theoretical sense. One of the things I noticed was the caption on the stoneware referencing dishwasher safe. How do you generalize to non-visual terms in the labeling to ensure that something that looks like a dishwasher safe vase and doesn't match something that isn't dishwasher safe but visually has the same view?
Okay, so how do I match these like visual picture to the particular phrase?
To a non-visual property.
Okay, to a non-visual property. So it's actually, if that is in your training data, right? The model already sees that, and the caption that it is fed with, right? It's about stoneware, and it has that kind of phrase. So it learned from that, and once it sees a similar object, then it knows that the following words, like stoneware something has higher probability compared to other words in your vocabulary, right? Because it sees that already before. So that's how it maps. And sometimes it confuses too, like the towel and the girl dress. It looks similar, so maybe it takes the dress as a higher probability as the next best word. But it will improve over time as it sees more data and more representative data of the whole data set.
And I can also understand your question in a larger sense of how do you actually operationalize this on a real, global retail website and making sure that you don't have the word dishwasher safe when it isn't. And if you're asking the question in that sense, this is just half of the solution. The other half, of course, involves more data. It'll generate better captions. But the idea here is to save a lot on the labor process of having, a million items handcrafted as far as captions by individuals. There has to be a QA process at the end, but of course the QA will cost a lot less than otherwise.
Okay. Well, thank you.